Hello and welcome to yet another lecture on Basic Electrical Engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is generation of rotating magnetic fields and construction of a three-phase induction motor. Lesson objective. After the end of this topic, students will able to understand the concept of generation of rotating magnetic fields and construction of a three-phase induction motor. So, generation of rotating magnetic fields and construction of a three-phase induction motor. Generation of rotating magnetic fields. So, in order to obtain the rotating magnetic fields, we will first imagine that stator of an electric motor have generally two parts. One is called the stator and one is called the rotor. So, stator of an electric motor, where the three-phase winding is physically distributed in the stator core in such a manner that the windings of each phase is separated from other by 120 degree in space. So, first of all, we will discuss what is phase. Phase means set of windings. Three phase means three sets of windings. They are separated in space by an angle of 120 degree. So, what is stator core? We will discuss later today about the stator core. Only now we will know that up till now we will only concentrate that a machine or electrical motor will have two parts. One is called the stationary part, that is stator, and one is called the rotating part, that is rotor. And this is a pictorial view of stator windings where that yellow portion is indicate the Y phase, blue portion indicates the blue phase, and red portion that is indicate the red phase. That is generally known as RYB phase. And it is clear from that particular figure that they are separated by an angle 120 degree in space. They are separated by an angle 120 degree in space, and phi r is the magnitude of the flux in R phase, where phi b and phi y stands for the magnitude of the flux at B and Y phase. So the three-phase windings are physically distributed in the stator core in such a manner that the windings of the each phase is separated from other by an angle of 120 degree in space. So we all know that the vector sum of the three currents in a balanced three-phase system is zero at any instant. So vector summation of the current in the three phases in a balanced three-phase system is always zero. But the resultant of the magnetic fields produced by the current is not zero. Rather than it will have constant non-zero value rotating in space in respect to time. So three-phase balance system. So the current in the three-phase balanced three-phase system is zero. That the sum of the three-phase currents at any instant. But the resulting magnetic field that is produced by the current is not zero. Rather than it will have a constant non-zero value rotating in space in respect to time. So the magnetic flux that is produced by the current in each phase can be represented by the equations. This is similar to the representation of a current in a three-phase system, that is in the R phase. The magnetic flux is phi m sine omega t. Phi m is the maximum value of the flux. In Y phase, the current is phi m sine omega t minus 120 degree. And phi b, that is in B phase, the current is phi m sine omega t minus 240 degree. So it is clear that in space they are 120-degree in apart, and in time domain they are also 120-degree apart from each other. Each of the fluxes are 120-degree apart from each other. So this is given that where the phi r, phi y, and the phi b are the instantaneous values flux of corresponding to red, yellow, and blue phase winding, where phi m is the amplitude of the flux wave. So the flux wave in space can be represented by this figure, that where this is the sine graph. So it is clear that R is in phase and another two, yellow and blue, are 120-degree apart. One is minus 120 degree and one is called plus 120 degree or minus 240 degree. They are apart from the R phase, and it is clearly seen that the blue phase and the yellow phase that are 120-degree apart from the red phase. So it is clear that one is sine omega t, phi m sine omega t, and another is, that is phi m sine omega t, and phi y is sine omega t minus phi y, that is the yellow phase, is sine omega t minus 120 degree, and phi b, the blue phase, is sine omega t minus 240 degree. So there is the graphical representation of a three-phase flux that we have seen. So let us start with the point 0. At point 0 point, so phi r became phi m sine omega t equal to 0 here. So phi m sine 0 equal to 0. The value of phi y becomes phi m sine 0 minus 120 degree, that is phi m sine of minus 120 degree. The value of phi y is equal to minus root 3 by 2 phi m for omega t equal to 0. And the value of phi b is phi m sine 0 minus 240 degree, that is phi m sine of minus 240 degree, that is root over 3 by 2 phi m. So when omega t equal to 0, the value of fluxes in the three phase, that is phi r is 0, phi y is minus root over 3 by 2 phi m, and phi b is root over 3 by 2 phi m. Putting those values in the previous equation, we will get the three equations. So the resultant if I see the pictorial view, it is clearly that the resultant of these fluxes at that instant, that is the phi r, phi suffix r stands for resultant, is 1.5 phi m. So this is the resultant value of the flux. So this is phi b, that is root over 3 by 2 phi m. This is phi y, that is minus root over 3 by 2 phi m, and they are separated by an angle 60 degree. If I use the conception of the vector in order to find the resultant value phi r, the phi r will be become phi 1.5 phi m, that is the phi r, the resultant value of the flux when omega t equal to 0 degree. This is the resultant value of the flux phi r equal to 1.5 phi m. And here it is clear that phi b and phi y is separated by an angle 60 degree. So now, on that particular graphical representation of the flux that we have seen, we will consider the point 1, and here the omega t equal to pi by 6 or 30 degree. We are applying the conception of omega t equal to 30 degree. So the value of phi r became phi m sin 30 degree, that is half of phi. The value of phi y, that is became phi sine of 30 degree minus 120 degree, that is equal to phi m sine of minus 90 degree, that is minus phi m. And the value of phi b became phi b equal to phi a sine of 30 degree minus 240 degree, that is equal to phi m sine of minus 210 degree, and it will become half of phi m when omega t equal to 30 degree. So the resultant of this flux, that is the resultant value, that is the phi y equal to minus phi m, phi r equal to half of phi m, phi b equal to half of phi m, and they are separated in space by an angle 120 degree. So the resultant of the flux, that is phi r, became 1.5 phi m. And it is clear from that previous picture and this picture that the resultant flux vector is rotated 30 degree further in clockwise without changing its value. So the resultant value, that is phi r equal to 1.5 phi m, it is remain same, but the difference is that the magnitude of the resultant flux phi r, that is remain same, but it's moved at an angle or rotates at an angle of 30 degree further in the clockwise direction without changing its value. So previous it was here, and now it is moved to the 30 degree in the clockwise direction when omega t equal to 30 degree. Now consider the point 2 on that particular graphical representation where omega t equal to 60 degree. The value of phi r now became phi m sin 60 degree, that is equal to root over 3 by 2 phi m. The value of phi y is phi y equal to phi m sine of 60 degree minus 120 degree, that is phi m sine of minus 60 degree, that is equal to minus root over 3 by 2 phi m. And the value of phi b became phi b equal to phi m sine 60 degree minus 240 degree, that is phi m sine of minus 180 degree, that is 0 degree. This is the pictorial view. So the resultant of these three flux, now if we see that phi y is became minus 3 by 2 phi m, phi r is became root over 3 by 2 phi m, phi r, and the resultant, that is became 1.5 phi m. So it is clear that the resultant of this three fluxes that instant is 1.5 pi m, which is shown in this figure, and it is clear that the resultant vector is rotate 30-degree further in the clockwise direction without changing its value. The magnitude remains same, but it is rotate in the direction in the clockwise direction by an angle of 30 degree when omega t equal to 60 degree. Now the point 3 of the graphical representation, where omega t equal to pi by 2 or 90 degree, the value of phi r, that is became phi m sine 90 degree, that is phi m. The value of phi y will become phi m sine 90 degree minus 120 degree, that is phi m of sine of minus 30 degree, that is minus half of phi m. And the value of phi b is phi b equal to phi n sine 90 degree minus 240 degree, that is phi n sine minus 150 degree, that is half of minus half of phi. So the resultant of this flux at that instant is 1.5 phi m, that we have generally seen the pictorial rule where phi b is minus half of phi m and phi y is minus half of phi n. So the resultant value, that is the phi r, is 1.5 phi m, and here it is clear that the resultant flux vector, the magnitude will remain same, that is phi r equal to 1.5 phi m, but the flux vector is rotate 30-degree further in the clockwise direction without changing its value. So again, it is clear that the phi r, that is rotated in the 30-degree clockwise direction without changing in value when omega t equal to 90 degree or pi by 2. So when omega t equal to 0 degree, this is the resultant value of phi r. When omega t equal to 30 degree, this is the resultant value of the phi r. When omega t equal to 60 degree, this is the resultant value of the phi r of the three fluxes, that is phi r. When omega t equal to 90 degree, this is the resultant value, that is phi r. So it is clear that for each of the angles 0 degree, 30 degree, 60 degree and the 90 degree, the resultant value, the magnitude will remain same, 1.5 pi m. But from that initial position, it is rotated in the clockwise direction by an angle 30 degree in each case. So it is clear that the magnitude of the resultant flux will remain same, but it is rotating in a direction of in a clockwise direction by an angle 30 degree for different values of omega t. For omega t equal to 0, it is there. For omega t equal to 30 degree, it is rotated by an angle 30 degree, keeping the magnitude same. For omega t equal to 60 degree, it is again rotated by an angle 30 degree, keeping the magnitude same. And omega t equal to 90 degree, it is rotated by an angle 30 degree, again in the clockwise direction, keeping the magnitude same. So due to the balance supply applied to the three-phase stator winding, a rotating or revolving magnetic field is established in space, that we have already seen that due to a balance three-phase supply that is applied on the stator winding, a revolving or a rotating magnetic field that is generated or established in space, because the magnitude of that rotating magnetic field is remain same, that is phi r equal to 1.5 pi m, but due to the different values of omega t, different instants, that omega t equal to 0 degree, omega t equal to 30 degree, omega t equal to 60 degree, omega t equal to 90 degree, and so on, the resultant flux that is rotating in the clockwise direction for each omega t value by an angle 30 degree means from omega t equal to 0 to omega t equal to 30 degree, the resultant flux rotates in the clockwise direction by an angle 30 degree, and so on. So from those four pictorial views, we can say that we are generating a rotating magnetic field that is generated when a balanced supply or a balanced three-phase supply is applied to the stator winding. A rotating or revolving magnetic field is generated in space. So another part of today's discussion is the construction of three-phase induction motor. So the three-phase induction motor is the most widely used electrical motor. Almost 80% of the mechanical power used by the industries is provided by three-phase induction motors because of its simple construction, low cost, good operating characteristics, and the absence of commutator and good speed regulation. For those above mentioned characteristics, almost 80% of the mechanical power that is used by the industries is supplied or provided by the three-phase induction motor. And those reasons are a simple construction, low cost, good operating characteristics, the absence of commutator, and good speed regulation. In three-phase induction motor, the power is transferred from stator to rotor winding through induction. The induction motor is also called a synchronous motor as it is runs at a speed other than the synchronous speed. So this is the basic of a three-phase induction motor. That why in industry the the three-phase induction motor is used widely, and how a power that is transferred for a three-phase induction motor, that is, the answer is that from stator to rotor winding through the induction. So like any other type, there is a construction part of the three-phase induction motor that, like any other type electrical motor, a three-phase induction motor is constructed from two main parts. They are namely as rotor and stator. Stator. So the as the name that is indicate that stator, from the name stator, this indicate that stator is the stationary part of an induction motor. A stator winding that is placed in the stator of induction motor, and the three-phase supply is given to it. So three-phase induction motor are formed or are constructed or having two main parts. One is called the stator. The name suggests that stator is the stationary part of an three-phase induction motor, and a stator winding that is placed in the stator of an induction motor, and the three-phase supply is given to it. And the rotor, the name that is suggested that the rotor is a rotating part of induction motor. The name that suggests indicates the rotor is the rotating part of an induction motor. The rotor that is connected to the mechanical load through the shaft. The name that is suggested that the rotor is the rotating part of a three-phase induction motor of an induction motor and rotor that is connected to the mechanical load through the shaft. So from that particular discussion, we have understood that three-phase induction motor has two parts. One is the stationary part, that is known as the stator, where a three-phase direct supply is provided, and one is the rotating part that is called the rotor, where the rotor that is connected to the mechanical load through the shaft. So the rotor of a three-phase induction motor are further classified as squirrel cage rotor and slip ring rotor or wound rotor or phase wound rotor. So depending upon the type of rotor construction used in the three-phase induction motor are classified as the depending upon the type of rotor construction used. The three-phase induction motor are classified as squirrel cage induction motor, slip ring, and the first one is the squirrel cage induction motor, and second one is the slip ring induction motor or wound induction motor or phase wound induction motor. So the construction of a stator for both of the kinds of these three-phase induction motors are identical. For both squirrel cage and slip ring induction motor, the construction of the rotor for this type of induction motors are identical. So the other parts of the three-phase induction motors are shaft for transmitting the torque to the load. This shaft that is made up of steel. Second one is the bearings for supporting the rotating shaft. Bearings for supporting the rotating shaft. One of the problems with electrical motors is the production of heat. One of the problems with the electrical motor is the production of heat during its rotation. To overcome this problem, we need a fan for cooling. For receiving external electrical connection, terminal box is needed. There is a small distance between rotor and stator, which is generally varies from 0.4 millimeter to 4 millimeter. Such distance is called the air gap. So the different parts of three-phase induction motor are the shaft that is generally used for transmitting the torque to the load and it is made up of steel. Bearings are there for the support of the rotating shaft. In order to, during the rotation, the general problem that is the motors are facing is the generation or the production of heat. To overcome this problem, a fan is there for the cooling purpose. For receiving the external electrical connection, terminal box is needed. And there is a small distance between the rotor and stator, which is generally varies from 0.4 to 4 millimeter. And such distance is called the air gap. So first we have seen the stator of three-phase induction motor, the stationary part of an induction motor. The stator of the three-phase induction motor that is consists of three main parts. First is called the stator frame. Second one is stator core. And third one is stator winding or field winding. So we'll start with stator frame. This is the pictorial view of stator frame. And it is clear that the name the frame from the particular name called stator frame, it is clear that It is the outer part of the three-phase induction motor, and its main function is to support the stator core and the field winding. It acts as a covering, and it provides protection and mechanical strength to all the inner parts of the induction motor. The frame that is either made of die-cast or fabricated steel. The frame of three-phase induction motor should be strong and rigid, as the air gap length of three-phase induction motor is very small, that we have already seen, that is from 0.4 to 4 millimeter. Otherwise, the rotor will not remain concentric with the stator, which will give rise to an unbalanced magnetic pull. So from the name, it gives us a clear indication that stator frame means it is the outer part of a three-phase induction motor, which are generally used to support the stator core and the field winding. So from that pictorial view, it is seen that it is acting as a covering, and it provides the protection and mechanical strength to all the inner parts of the induction motor, and it is generally made of die cast or fabricated steel. So this is the general purpose of a three stator frame of a three-phase induction motor. And the frame of a three-phase induction motor should be strong and rigid, as the air gap length of the three-phase induction motor is very small. Otherwise, the rotor will remain concentric with stator, which will give rise to an unbalanced magnetic pull. Second one is the stator core. This portion, that is the portion which is fitted here, the core of the stator. The main function of the stator core is to carry the alternating flux that we have already seen. In order to reduce the eddy current loss, the stator core is laminated. This is the pictorial view of stator core. These laminated types of structure are made up of stamping, which is about 0.4 to 0.5 millimeter thick, a stamping. This portion will be fit here. All the stampings are stamped together to form a stator core, which is then housed in stator frame. Here, this portion is housed here, stator frame. The stamping is made up of silicon steel, which helps to reduce the hysteresis loss occurring in the motor. So the main function of the stator core, which is fit here or housed in the stator frame, and the main function of the stator core is to carry the alternating flux. And the stator core, in order to minimize the eddy current loss, stator core is laminated. And these laminated types of stator structure that are made up of stamping, which is about 0.4 to 0.5 millimeter thick, and the stampings are made of with silicon strings, which helps to reduce the hysteresis loss that is occurring in the motor. So another is the stator winding. This is the pictorial view of the stator winding that we have seen. This is the pictorial view of the stator winding. So the slots on the periphery of the stator core of a three-phase induction motor carry the three-phase winding, that is slots that is provided in the stator core that will carry the three-phase windings. Those slots, those slots are carrying the three-phase windings. We apply three-phase AC supply to this three-phase winding, that is the stator winding or the field winding. The three phase of the windings are connected either in star or delta depending upon which type of starting method that we use. We start the squirrel cage motor mostly with star delta stator, and hence the stator of the squirrel cage motor is delta connected. Because we start the squirrel cage motor mostly with star delta stator, hence the stator of the squirrel cage motor is delta connected. We start the slip ring three-phase induction motor by inserting resistance. So the stator winding of slip ring induction motor can be connected either in star or delta. The winding wound on the stator of the three-phase induction motor is also called the field winding, and when this winding is excited by three-phase AC supply, it produces a rotating magnetic field that we have already seen. That a rotating magnetic field that is generated when a three-phase balanced AC supply is provided. And this winding wound on the stator of the three-phase induction motor is also called the field winding. And when this field winding is excited by a three-phase AC supply, balanced AC supply, it provides a rotating magnetic field. So this is the general information about the stator winding or the field winding of a three-phase induction motor. So there are another part is called the types of three-phase induction motor. First one is the squirrel cage three-phase induction motor. This is the pictorial views of squirrel cage three-phase induction motor. So the rotor of the squirrel cage three-phase induction motor is cylindrical that we have seen in this picture. It is cylindrical in nature and have slots on the periphery, and that the slots are provided on the periphery. The slots are not made parallel to each other but a bit skewed. There is the rotor bars are there that is slightly skewed, and those are the end rings where the rotor bars are short circuited or connected. And it is clear that they are from that particular figure that the slots are not made in parallel to each other but are bit skewed, as the skewing that is prevents the magnetic locking of stator and rotor teeth and makes the working of the motor more smooth and more easy. The squirrel cage rotor consists of aluminum bars or copper bars, and these aluminum bars, copper bars are called rotor conductors and placed in the slots on the periphery of the rotor. The rotor conductors are permanently shorted by the copper or aluminum rings that is called the end rings. That is called the aluminum or the copper rings are known as end rings. To provide the mechanical strength, these rotor conductors are braced to the end rings and hence from a complete closed circuit that is like a cage, and hence it got its name as squirrel cage induction motor. So this is the squirrel cage induction motor, which is from which is like a cage. So from that the name is came squirrel cage induction motor. Squirrel cage rotor winding is made symmetrical as the end rings permanently short the bars. The rotor resistance is quite small, and it is not possible to add external resistance as the bar gets permanently shorts. So there is no chance to provide the external resistance as the bar that is gets permanently shorted. The absence of slip ring and the bar brushes that is make the construction of the squirrel cage three-phase induction motor very simple and robust and hence widely used three-phase induction motor. This motor have the advantages of adapting any number of pole pairs. And the diagram that is shown a squirrel cage induction motor having aluminum bars that is short circuited by the aluminum end ring. So this is an pictorial view of the three-phase squirrel cage induction motor. So the squirrel cage induction motor, what are the advantages of squirrel cage induction motor? So the construction of the three-phase induction squirrel cage induction motors are very simple and rugged. And the second one is that as there are no brushes and the slip rings, this motor requires a less maintenance. So the application of squirrel cage induction motor are we use the squirrel cage induction motors in lathe, drilling machines, fan, blower, printing machines, etc. This is a pictorial view of three-phase induction squirrel cage induction motor, where it is the end bell, these are the bearings, this is the rotor, this is the fan blades for the cooling purpose, the stator, the wiring cover, the motor frame, and the end bell. So this is the general pictorial view of squirrel cage three-phase induction motor. So another is called the slip ring or wound rotor three-phase induction motor. This is a pictorial view of slip ring, and here is a slip ring is given on the shaft of the motor. So this in this type of three-phase induction motor, the rotor is wound for the same number of poles as that of the stator, but it has less number of slot and has fewer transfer phase of a heavier conductor. The rotor also carries star or delta winding similar to that of the stator winding. The rotor that is consists of number of slots and rotor windings are placed inside these slots. The three end terminals are connected together to form a star connection. As its name indicates, this phase, three phases, slip rings induction, three-phase slip ring induction motor that is consist of slip ring connected on the same shaft as that of the rotor. This is the rotor shaft, those are the windings, these are the brush, and this is the slip ring that is connected or mounted or say connected on the same shaft as that of the rotor. This is a rotor shaft and slip rings are mounted or connected on the same shaft of that rotor, but slip rings are mounted and the brushes are there. Brushes are mounted on the slip rings. This is the rotor core and this is the rotor shaft, core of the rotor, and these are the windings. This is a slip ring that is mounted on the rotor shaft and the brushes are mounted on the slip rings. So the three ends of the three-phase windings are permanently connected to the slip rings. There is a slip ring induction motor. This is the star connected rotor winding and this is the rotor frame, and it is clear that the three ends, first, second and the third end, those are connected to the three slip rings 1, 2 and 3. The external resistance can easily be connected to the brushes. These are the brushes and this is the shaft, and the external resistance that is connected through the brushes and the slip rings and hence used for the speed controlling and improving the starting torque of the three-phase induction motor that we have already seen. But with the help of the external resistance, we can improve the starting torque of the three-phase induction motor, and we can also do the speed controlling. And here these the three external resistance are connected in RYB phase of the brushes through the brushes and the slip rings. With the help of these brushes and the slip rings, these three external resistance are connected to the star connected rotor winding. The brushes that are generally seen here are used to carry the and current to and from the rotor winding, that will carry the current to and from the rotor winding. These brushes are further connected to three-phase star connected resistance that we have already seen. So this is an electrical diagram of a three-phase induction star connected induction motor. So the purpose of the slip rings and the brushes that is given in a three-phase induction motors to connecting the external resistance in the rotor circuit. The resistance that are used to increase the starting torque is resistance. The external star connected rheostat that are generally used to increase the starting torque and decrease the starting current from the supply to control the speed of the motor. This is also an advantage of a slip ring or wound rotor induction motor. So the slip ring or wound rotor induction motor had some advantages, that is, it has high starting torque and low starting current. So possibility of adding additional resistance to control the speed. So application of a slip ring induction motor, or the slip ring induction motor are used where the high starting torque is required, that is in hoists, cranes, elevator, etc. So we are putting a difference between the slip ring and the squirrel cage induction motor. So for the slip ring induction motor, construction is complicated due to presence of slip ring and brushes. For the squirrel cage induction motor, construction is very simple. For the slip ring motor, the rotor winding is similar to stator winding, but for the squirrel cage, the rotor consists of rotor bars which are permanently shorted with the help of end ring. So for slip ring induction motor, we can easily add rotor resistance by using the slip ring and the brushes that we have already seen. For squirrel cage, since the rotor bars are permanently shorted, it is not possible to add the external resistance. So for slip ring or phase wound induction motor, due to the presence of external resistance, high starting torque can be obtained. But for the squirrel cage induction motor, starting torque is low and cannot be improved. Slip rings and brushes are present for the slip ring motor, that is why the name called the slip ring, and slip rings are and the brushes are absent in case of the squirrel cage induction motor. So frequent maintenance is required due to the presence of brushes for the slip ring induction motor. For squirrel cage, less maintenance is required. The construction is complicated and the presence of brushes and the slip rings make the motor more costly for the slip ring induction motor. For the squirrel cage, the construction is simple and robust and it is cheap as compared to the slip ring induction motor. The motor is rarely used, only 10% industry uses slip ring induction motor. Due to the simple construction and low cost, the squirrel cage induction motor is wisely used in industry. So the rotor copper losses are high and hence less efficiency for the slip ring or the phase wood induction motor. For the squirrel cage, the less rotor copper loss and hence high efficiency. So speed control by rotor resistance method is possible for slip ring induction motor. For squirrel cage, speed control by rotor resistance method is not possible. For the slip ring, induction motor are used when the high starting torque is required, that is in hoist, crane and elevator, etc. Hoist, crane and elevator, etc. For the squirrel cage induction motor is used in lathes, drilling machine, fan, blower, printing machines, etc. So there's a difference between the slip ring and the squirrel cage induction motor. So today we have seen the generation of rotating magnetic field and the construction of three-phase induction motor. Thank you.